Greetings to all. In the last lectures, we have discussed the design equations in terms of volume product, right. In that equation, we have not considered the stator geometry, like what is the stator outer diameter, what is the rotor outer diameter, rotor inner diameter, as well as slot geometry or slot area, and then flux densities at the back iron and flux densities in the teeth we have not considered. Only we considered at the air gap what is the flux density, what is the current density, and what is the inner diameter of the stator. Based on those three variables we have defined the power equation, right. So, in order to include the flux densities at the different parts of the stator and rotor and slot areas of the stator as well as rotor, and stator outer diameter as well as rotor outer diameter and rotor inner diameter, all these geometries, and along with that actual current densities. Like if we will see, the actual current density is happening inside the slot, right, more current density. So, with respect to the actual current density, we will derive the power equation. So, from that power equation we can find the physical dimensions of a machine, like outer diameter as well as inner diameter of the stator and length of a core. Okay. Let us consider a 3-phase machine. We can see here 3-phase machine having a outer diameter of d0 s and inner diameter dis, and inner diameter of the rotor is nothing but dir, and d0 r or d outer diameter of the rotor, okay, and Lg is the air gap diameter, sorry, air gap length. Lg is equals to air gap length. In the previous analysis we have not considered the slot geometry and we have not considered the outer diameter of the rotor, right. In this analysis, to find the accurate power equation, we will consider the flux densities at the back iron, that is Bc, and flux densities at the teeth, that is Bt, and flux density at the air gap, that is Bg value. So, we will see the all possible magnetic flux densities at different parts of the iron. Here we can see that the maximum flux density will happen in this region, right, where the area is less. In this region we will see the maximum flux density, right, as compared to the air gap, as compared to the core, this portion. This portion is the core portion and this portion is the air gap, okay. This is the core portion. So, flux densities at the different parts we will consider, and along with that thing we will see the actual area of the slot. We will consider the actual slot dimensions, like slot area if you want to represent, then this is the slot area. Okay. So, by considering this slot area, we will derive the power equation in terms of d3L product. This is the slot area AS, and the slot dimensions we can see here. Back iron length is DC and the radius from this portion to this portion, okay, from this point to this point, the radius is R2, and this portion is ds, and similarly this one is R1, and between this gap is nothing but d0 and air gap length is Lg, and the width of the teeth is nothing but t, small t, and the inner diameter is dis and outer diameter is d0 s. These are the different dimensions of the stator core. So, by considering all these dimensions, we will find the power equation in terms of B values and then electric loading values and then slot dimensions. Okay. So, Bg, Bt and Bc, different flux densities we will consider for deriving the power equation. So, first we will see the flux densities at the different portions of a stator core. Okay. We will see the flux lines, how the flux lines are flowing. So, here flux lines are coming in this manner. Okay. And in the core back iron, the flux lines are in this manner. Okay. So, our first task is to identify what is BC, what is BT and then what is BG, flux at the core and flux in the teeth and flux in the air gap, and along with that find the slot area. Okay. First step, I will start with the flux density at the air gap. Peak flux density, that is Bg peak, we have to find in terms of flux. In the average flux in the core, average flux in the teeth, average flux in the air gap, it will be same. Okay. The flux inside the core will be same. If we will neglect the fringing and everything, then flux in the core also is same. Okay. Now, in order to find the flux density maximum at the air gap, consider the flux average is equals to 2 by pi flux peak value. Okay. Here flux in terms of B and A we can write it B G peak into A. Okay. Area A is nothing but area of cross section with respect to that particular flux lines. Okay. Here area is nothing but Bg peak value into pi d dis into Le by P. This part is with respect to the x and this part is with respect to the y. X into y we can get the area with respect to the cross sectional area for air gap flux. Okay. Just find the area here with respect to this flux lines perpendicular cross sectional area, that is pi d by p with respect to the one particular pole and Le is the length of a core. Then Bg value is equals to Bg peak equals to flux average into P divided by 2 into dis into Le. This is equation number 1. Okay. Next we will find the flux density at the teeth. So, generally the teeth area will be smaller, right, we can observe in this figure. So, the teeth area is nothing but this one, the teeth area is smaller, right. So, because of that reason the flux density will be higher in the teeth portions. Okay. We will find that value exactly, what is flux density at the teeth peak value. So, again flux at the teeth is nothing but average is equals to 2 by pi phi t peak value. So, here 2 by pi is constant, flux is nothing but B into A, Bt peak into area is nothing but cross sectional area with respect to this portion we have to calculate. So, here cross sectional area with respect to this particular point is nothing but y axis is length into some stamping factor Ks. Here Ks is the steel stamping factor or steel stacking factor, okay. And Le is the effective length of a core including the air ducts, and y axis length is what? T is width of a single teeth, like that n number of teeth are there in the on the stator circumference. We can see here T is the width of one particular teeth, one particular teeth width is T. So, like that how many teeths are there under one pole or how many teeths are there under over a circumference is nothing but Qs is nothing but number of stator slots into T, then teeth length we have identified in a complete stator circumference. Per pole if you want, then by P we have to add, okay. This is the total area, then 2 by pi Bt peak Qs into T Le Ks divided by P, this is the average flux at the teeth. So, maximum flux density at the teeth is nothing but pi by 2 into flux average into P divided by Qs T into Le Ks. So, the flux average I am considering same. So, phi t average or phi c average or phi g average, all things I am representing as a phi average, okay. So, this is equation 2. Next, what is the flux density at the core or back iron? So, look at here the lamination of the stator core, this is the back iron, this one above the slots, this portion from here to here is the back iron, okay. So, how to find the flux density at that particular point? We will see the area where the flux lines are coming. This is the place where the maximum flux lines are entering into the teeth, right. So, we have to find the area with respect to that particular point, okay. Now, the flux core average value is nothing but 2 by pi flux at the core peak value, that is 2 by pi Bc peak into A. Here A is the area of cross section. In order to find the area of cross section, y axis length is nothing but Le into Ks. Le is the effective length of the core and Ks is the steel stacking factor, and x axis direction we are finding with respect to this manner, right, perpendicular cross sectional area. X axis length will be pi into d naught s minus pi into d naught s minus 2 dc, this value is dc, the back iron width, by 2, mean we have to take. Then this will result in dc value, pi into dc into Le into Ks is the area. Okay. Then the final equation with respect to the phi c average is nothing but 2 by pi into pi dc back iron width, length of a stator core and steel stacking factor into Bc peak. That results in Bc peak equals to phi average divided by 2 into dc into Le into Ks. Okay. This is equation 3. Now we have calculated the flux densities at the different parts, Bg at the air gap, Bt at the teeth, Bc at the core. Since the area with respect to the teeth is higher, so Bt value is greater than the Bg, and next Bc, and Bc is greater than Bg value with respect to the flux is same and area is different for different portions. So based on that relation we can conclude that the maximum flux density will happen at the teeth, the maximum next flux density at the core, and the next case will be at the air gap. Now we will see the ratios like Bt max flux densities at the different portion, what is the ratio, Bg by Bt is nothing but equation 1 divided by equation 2. It will result in P into phi average divided by 2 dis into Le divided by pi by 2 flux average into P divided by Qs into T into Le into Ks. Then this ratio will be Qs into T Ks divided by pi into dis. Just rearrange the terms. Finally, the teeth width we have to solve. So the teeth width is equals to Bg by Bt constant value into pi into dis divided by Qs into Ks. This is equation number 4. We have find the teeth width. Similarly, find the back iron length or back iron width dc by taking the ratio of Bg by Bc. Okay. That is equals to equation 1 divided by equation 3. So finally, after solving this expression we will see dc is equals to back iron length Bg by Bc constant into inner diameter of the stator divided by number of poles into steel stacking factor. This is equation number 5. Now consider the slot dimensions. Okay. We will take the, we will go back the same image. Here analyze the slot area as well as different diameters. See here we have to analyze the dimensions with respect to the rotor as well as stator and slot dimensions. So the slot dimensions we can see here with respect to the different parameters, how the slot dimensions are there, and with respect to the stator outer diameter as well as inner diameter, we can write the equations in terms of dis and d naught r and slot dimensions. So that is outer diameter of the stator is equals to inner diameter of the stator plus 2 into d naught is the slot opening height plus R1 plus ds plus R2 plus dc, and d naught r outer diameter of the rotor is nothing but dis minus 2 lg. This is equation number 6. Okay. These equations I have derived from the figure, from the slot image figure we can see here. So, this value is dc r2 and then ds and then r1 from here to here, and slot opening is d naught and remaining one is the lg value. Okay. Now, perimeter of the slot with respect to the W1. So, if I want to calculate the perimeter in this line, okay, where W1 and T we know, width of the teeth as well as width of a slot at the bottom side we know. That means the perimeter of the stator in terms of W1, Qs into T plus W1 is equals to dis plus 2 into d naught plus r1 into pi, right. So, here Qs is the number of slots into T plus W1 is nothing but this width. So, like this how many widths are there? Qs. So, Qs into T plus W1 is nothing but the perimeter, actual perimeter. We know that dis plus 2 d naught plus r1, okay, this length we know, okay, up to this point length we know, right. Up to this point, that is dis, the remaining one is nothing but 2 into d naught plus r1, add that thing into pi is nothing but circumference. This is equation 7. Similarly, the perimeter with respect to the W2 at the slot top side at this particular point, okay, where W2 we know and T also we know. Qs into T plus W2 is equals to d naught s, in terms of d naught s we can write it, right, d naught s minus 2 into d naught dc, right, back iron length dc plus radius at the bottom side of the slot into pi is equation number 8. Okay. Or we can write in terms of dis also. Dis means plus the remaining terms d naught plus r1, this is d naught, and ds r1 r1 up to r1 we have to write ds into pi. These two comes under same equation number 8, 8a and 8b. Okay. We have find the perimeter or circumference with respect to the W1 and W2. Okay. These equations involves in inner diameter of the stator as well as outer diameter of the stator d naught s, okay, and slot geometry. Slot geometry we can see the slot opening and the radius at the bottom side of the slot, that is this one. This radius is nothing but r1 and this radius here is nothing but r2. Okay, we can see here this radius is nothing but r2, this radius, and this radius is nothing but r1. Next task is to find the area of the slot. Now we have calculated the flux densities at the different parts and the slot information. Now area of the slot we will find. So the slot we have considered in this manner, right. this is the slot dimensions. From here to here it is DC, and from here to here it is R2, this is DS, and from here to here R1, and this is D0. We have to find the slot area, this area we have to find. So, for easy analysis we can split this area into 3 parts. The first part will be in this manner, and second part will be in this manner, and third part will be in this manner. Okay. So, it is a trapezoidal kind of thing. Okay. So, calculate the area for this thing. This height is ds, and it is W2 and it is W1. So, W2 into ds minus the total square area minus the 2 times the half BH area, the triangle area is nothing but this one. This we have to remove from the square area. So, 2 into half BH, that is nothing but W2 minus W1 by 2 into ds. Here one more by 2 will come with respect to the half BH, then it will result in W2 plus W1 by 2 into ds. Okay. And the second case, here the radius is R2 and here also R2, and this is W2 minus 2R2, this width, whatever the width is there, W2 minus 2R2. Calculate the area of this portion as a rectangle, and this portion again arc. So, this area you just split into 3 parts. This is part 1 and this is part 2 and part 3. So, this we can write it as pi R2 square by 4 plus again the third point is pi R2 square by 4, and the second part is nothing but rectangle, right, W2 minus 2R2 into R2 height again. Similarly, third case also, from here to here R1 and here also R1, this region consider it as a rectangle, okay, and calculate the area. So, if we will club all these 3 terms, one, 2 and 3, then area of the slot is nothing but final equation W1 plus W2 by 2 into ds plus W2 minus R2 into C1 into R2 plus W1 minus R1 C1 into R1. This is equation number 9. Here C1 is a constant which is equals to 2 minus pi by 2. Solve this term 1 and term 2 and term 3 with respect to the different areas. Then final area of the slot we will get in this manner. Okay, this is the area of slot. Okay. From equation 9 and equation 4 to 8, we have to find now what is W1 and W2 and what is T and what is ds. All these things we have to substitute in area of the slot equation, that is equation number 9. So, equation 9 involves the W1 and W2 and ds, and these 3 are the unknowns. So, W1 and W2 and ds we have to find equations and then we have to substitute there. First we will start with W1, that is the width of the stator slot at the bottom side. So, from the equation 7 and equation 8 we can find W1 and W2, right. Just rearrange the terms from equation 7 and 8, then we can get the W1 is equals to pi by Qs into dis inner diameter of the stator into 2 into d naught plus r1 minus t. In this equation we know the value of T, right, from the flux density ratios. In equation 2 and 3 and 4 we have discussed the different flux densities and we have taken the ratios, right. The T value is nothing but this one, equation 4. Here we can see the T value and DC value also, okay. Back iron value also, that is equation 5. So, from equation 4 and 5 we can substitute the DC value and final W1 is nothing but pi by Qs into dis plus 2 into d naught plus r1 minus T is nothing but dis into pi divided by Qs into Ks, steel stacking factor, Bg by Bt. This is the T value. Now define Bg by Bt into 1 by Ks as a constant of Gt, okay. Then W1 is equals to pi by Qs into dis into 1 minus Gt plus 2 into d naught plus r1. This is equation number 10. Similarly, W2 we have to find in terms of d naught s and dis. W2 is equals to, from the equation number 5 and 8 and 7, then pi by Qs into d naught s minus 2 into dc plus r2 minus t. Equation number 5, 7 and 8. Eighth equation is this one and fifth equation is with respect to the DC, okay, and seventh equation is this one. So, from these three equations we have rewritten the W2 terms and then substitute the T value as well as DC value here. Here 2 DC is nothing but 2 into dis into Bg by Bt from the equation 4 or 5, I think. This Bt by Bg by Bc value we have derived, right, divided by Ks into P. Here also these multiple values we can define it as a Gc, some constant, and already T has some constant, that is T equals to dis into pi by Qs into Ks Bg by Bt. Here also the constant we have assumed, this is Gt. Substitute these values in this equation and finally we will end up the W2 equation pi by Qs into d naught s minus dis into Gt plus Gc minus 2R2. This is equation number 11 with respect to W2. So, from equation 7 and 8, Okay. We have find the perimeters, right, with respect to W1 and T and D naught S and other things. Find the W2 minus W1, okay, that is equals to pi by Qs, or we can say directly equation 7, equation 8 minus equation 7, okay. Then we can see the final outcome pi by Qs into D naught S minus 2 into dC plus R2 minus DIS minus 2 into D naught plus R1. So, these terms with respect to the equation 8 and these terms with respect to the equation 7. Okay. Finally, pi by Qs D naught S minus 2 into D naught plus R1 plus R2 plus DC minus DIS, right. So, this entire term we can replace with 2 into ds, right, from the slot diagram if we will see. So, here dis plus d naught plus r1 plus ds plus r2 plus dc, all these terms if we will add 2 times to the inner diameter of the stator, then we will get the outer diameter, right. So, in with respect to that analysis, we can get here the total term is nothing but ds. Then finally, ds is equals to W2 minus W1 by 2 pi into Qs. This is equation number 12. Okay. Now, we have to substitute all these values in the equation 9, that is the slot area. So, slot area equation is this one. Substitute W1, W2 and then ds value. So, slot area equation is this one. Here W1 we know, W2 we know, W1 is nothing but equation number 10 and W2 is nothing but equation number 11 and ds is nothing but equation number 12. Substitute these 3 equations in 9, then area of the slot is equals to W1 plus W2 by 2, ds is nothing but W2 minus W1 into Qs by 2 pi from the equation 12 plus remaining term I am rewriting as it is. Okay. Let us consider this is term 1 and term 2. Okay. Solve these 2 terms by substituting W1 is equals to pi by Qs into ds, dis is nothing but inner diameter of the stator, 1 minus gt is a constant plus 2 into d naught plus r1. This is the equation for W1 and equation for W2 is pi by Qs d naught s minus dis into gt plus gc minus 2 into r2. Okay. This is with respect to the equation 10 and this is with respect to the 11. Those 2 equations we are substituting in the area of the slot equation. At the end the term 1 in the slot area equation is nothing but pi by 4 Qs into d naught S, that is outer diameter of the stator, square, plus dis inner diameter of the stator, square, plus gt plus gc whole square, minus 2 into d naught S and dis into gt plus gc. Here gt and gc are the constants, plus 4 r2 square minus 4 r2 into d naught S minus dis into gt plus gc minus dis square into 1 minus gt square minus 4 into d naught plus r1 square minus 4 capital dis into 1 minus gt into 1 d naught plus r1. This is the total equation with respect to the term 1. Then term 2, this final equation will be equals to 4 pi by 4 Qs into dis square into gt plus gc square minus 1 minus gc square minus 2 dis and d naught S into gt plus gc plus d naught S square, okay, plus r2 square pi by qs minus pi by qs into r2 d naught S plus pi by qs r2 dis into gt plus gc minus pi by qs into d naught square plus r1 square plus 2 d naught r1. I am expanding the above equation. So, final equation of term 1 with respect to all terms we can see here, and then term 2 is with respect to the slot dimensions, right, that is W1 and into R1 minus 2 minus pi by 2 into R1 square plus W2 into R2 minus 2 minus pi by 2 into R2 square. Here 2 minus pi by 2 is nothing but C1 we have considered, right, while discussing the slot area. Here we can see the C1 is a constant, that is 2 minus pi by 2. The same thing I considered here. Just substitute W1 and W2, add term 1, that is equation number 12 and 13. Okay. So, these two equations will be 13 and 14. Substitute 13 and 14 in slot area. AS equals to the final equation pi by 4 QS into dis square, that is inner diameter of the stator, into gt plus gc square minus 1 minus gt square minus 2 into inner diameter of the stator and then outer diameter of the stator into gt plus gc constants plus d naught s square. Okay. This is the equation with respect to the first term, and then remaining terms with respect to the slot dimensions r2 square into minus pi by qs plus pi by 2 minus 2 minus pi by qs into d naught square minus r1 square into minus pi by qs plus 2 minus pi by 2 minus pi by qs into dis into d naught into 1 minus gt four qs by pi. I am multiplying to make the common bracket with respect to the total equation. Okay. Just 4 qs by pi and outside pi by 4 qs I am taking it common. Then final equation we can see as, that is slot area, is equals to in the form of pi by 4 qs into f of lambda plus some constant term, the second term from this point to this point, this complete term I am representing as a x, and from here to here I am representing as a function f of lambda, second order equation. Okay. Then f of lambda is equals to as into 4 qs by pi minus x will come. So, minus x term I am replacing with plus delta. Okay. As into 4 qs, qs is the number of slots by pi, minus x I am replacing with plus delta. Here delta is equals to 4 r2 square minus 2 qs r2 square plus 8 qs by pi into r2 square plus 4 d naught square minus 4 r1 square plus 8 qs by pi r1 square minus 2 qs r1 square plus 4 into dis into d naught into 1 minus gt. This is the total equation for delta. It is a constant. This delta is also equals to minus x. Okay. So, this is the final equation with respect to the function f of lambda, the equation number 14 or 15. This is the equation number 15. This function represents the copper function, how much amount of copper we are utilizing in the electrical mission, because this f of lambda function depends upon the slot area, number of slots and slot geometry. Okay. Slot area we have considered, and number of slots and slot geometry and bg value, bt value and bc value. We can see here with respect to the stator slot, this is the stator lamination where we have considered the flux densities at the different parts of the core. Okay. F of lambda is nothing but, it is a second order equation. I am representing with a lambda square minus 2b lambda plus 1. Okay. Here a is nothing but gc plus gt square minus 1 minus gt square, b is equals to gt plus gc, and then lambda is equals to dis by d naught s. And one more thing here, we have to take it d naught s common in this equation, and f of lambda into d naught s will come here, d naught s square. So, this side it will be d naught s square, and f of lambda equals to pi into d naught s square and delta divided by d naught s square. This is the final equation. Okay. F of lambda final equation is nothing but as into qs divided by pi d naught s square by 4 plus delta divided by d naught s square. This is the equation number 15. I have rewritten the equation. This equation involves the all slot geometry as well as slot area and different flux densities at different parts of the core. With this, I am concluding this class. In this lecture, we have discussed the D3L sizing equations, where we have considered the slot geometry as well as different flux densities of the iron core. Like we can see here the flux densities at the back iron, flux densities at the teeth, and the slot area, everything we have considered to realize the sizing equations. Thank you.